Now we're going to look more specifically at those energy states and the energy associated with those energy states. It starts with Bohr and the theory of hydrogen is he's trying to explain why the electrons don't just spiral in to the nucleus and then bind to the nucleus. Why does not those Coulomb forces just take over? So he included both the classical models and non-classical ideas in an attempt to understand the atom. So Bohr's assumption for hydrogen, which we know isn't right, but here we're going to assume that the electrons do follow circular paths. Why this is useful is we can ultimately get a radius of the atom, try to figure out how big it is. So first we're going to start with a basic energy balance, that we have our basic orbital equation. This looks very much like the orbital equation we do for a satellite in space, except we have the centrifugal force is caused by the Coulomb force, so we have our Coulomb's force in there, and then our energy level that we talked about. So these are the exact same equations that we started the class with to be able to describe how this electron is basically orbiting the central nucleus. But only certain electron orbitals are stable, which is not explained by these equations. These orbitals do not emit energy in the form of electromagnetic radiation as they're going around because they're accelerating, right? We said that all light is created when a charged particle decelerates or accelerates. And in order to accelerate, you need to absorb a photon. To decelerate, you need to give off a photon. These electrons, as they go around the atom, we would think are experiencing centripetal acceleration because the direction of the velocity vector is always changing. So classical mechanics just doesn't work in this case. So what does work? Well, the radiation is emitted by the atom only if we jump to different energy levels, that the energy level is stable, that there really isn't an acceleration going on. And that's why we now think of electrons as being in a cloud. They're not really going around per se. So the jump cannot be treated classically. And so this is another reason for modern physics. So generally, not the same as the frequency of the electron's motion, and the frequency is given by hf. So the size of the electron orbits is determined by the condition imposed by the electron's orbital angular momentum rather than its pure energy state. So what are the ultimate results? Is the electron's angular momentum is the mass of the electron times its velocity times its radius, and that we're going to set equal to an integer times a constant. So we're going to have a constant h with a bar on it is simply the h we've seen before divided by 2 pi. The total energy of the atom is a combination of the kinetic energy and the potential energy, the same potential energy equation that we saw in chapter 15. And so if we combine those, the total energy state of any given electron is given by this equation. And we can use that if we model the electrons as being in orbit to find an orbit radius for the atom. This is useful to get a rough idea of what the size of this atom is. This is based heavily on the assumption that the electron can be only certain orbitals determined by the integer. When n equals 1, we're in the lowest energy state, and so that's called the Bohr's radius of the atom, the lowest energy state. Clearly, the atom can basically swell as it absorbs energy, and those electrons move to higher and higher energy states. And so we can calculate, most of these things are constants, so we have n equals 1. This is a constant, h bar is a constant, the mass of electrons constant, Coulomb's constant, and the electrons. So we can calculate the radius, and so that fundamental radius is another constant given by the Bohr's radius, which is 0.0529 nanometers. And so we know what that is, so we're going to call that A0. We could separate out the n because n was 1 when we did that calculation initially, so we can separate that out into a different constant. Therefore, the energy level of any orbit is this value. So that's exactly from our calculation with these constants, which is this group of variables times 1 over n. That means we can calculate the energy difference between movement between any one energy state and any other energy state. This looks very much like our Rydberg equation, except we have a different constant, which is the energy state of that ground state, and we're calculating the change in energy rather than the wavelength giving off. So let's get some practice with these equations. And so here we have a hydrogen atom is at its first excited state, so that means n equals 2. For this particular atom, we're going to use the Bohr theory of the atom in order to calculate the changes in energy and the orbit and the total energy. So we're going to start out with the radius of the orbit. We'll start out with this equation. So I'm not going to use the equation with all the constants in it because, hey, we figured out what all those constants are. So we want r equals, so we want the second r. So r with n equals 2 is equal to 2 squared times a naught, 0.0529 nanometers. So I get 0.2116 nanometers is the radius of the atom if it's in its first excited state. Then I can find the velocity of the electron. So I'm going to start with simply F equals ma. Should be an equation you're familiar with. That force is again the Coulomb's force, so I can type in the Coulomb's equation, Q plus, Q minus, over Rn squared is my radius of my atom, is equal to my kinetic energy, the mass of my electron, times Vn squared over my radius for my centripetal acceleration. And then I can solve that for the velocity at any given end state is equal to the square root of my Coulomb's constant, E squared. Remember, this is a proton and an electron, so their charges are just E, and the mass of the electron times the radius of n squared. So this is mass times acceleration, with again that being centrifugal acceleration. I know equations from fall semester, so it's been a while. And so now I have an equation where I can just put the numbers in. Ke again was the 8.99 times 10 to the 9th coulombs. I'm sure you remember from the very beginning of the semester. Here I have my mass of my electron, the charge of my electron, the mass of the electron, and the radius. So I get that these electrons must be traveling at 1.9 times 10 to the 6 meters per second, which is perfectly allowed, because it's much, much slower than the speed of light at 3 times 10 to the 8th meters per second. So not even all that close to the speed of light. Okay, so we got A's and B done. So A was the radius and B is the velocity. Well, now we want to find the total energy of that particular orbit. So the energy equation was Ke squared over 2r. So we're just going to plug our numbers in there. That is our same Coulomb constant that we had from way back at the beginning of the semester, times 10 to the 9th Newton meter squared per Coulomb squared. And then our charge on an electron, 1.6 times 10 to the negative 19th Coulomb squared, all divided by 2. Came from the equation 0.2116 times 10 to the negative 9th meters, and that gives us the number. Happens to be 5.44 times 10 to the negative 19th joules, or the 3.4 electron volts, which is what we said was the energy level of that second energy state. Now, finally, we want to calculate the change in energy from one state to another. Here we're going from the n equals 3 state to the n equals 2 state. I use this equation very much like I did the one for the wavelengths, that I just put my integers in. And since the ground state is 13.6 electron volts, never mind that we'll have the 2 squared in here. The 2 squared corrects for the energy level we're going to. So we simply do 16.3 electron volts times 1 over 2 squared minus 1 over 3 squared, and I get that it's gone, changed in energy level by 1.89 electron volts. And that's the end.